Hello and welcome everyone. Thank you for joining me today. My name is Arvind Krishnan and this webinar is about optimization of an aircraft frame. A little bit of background about myself. I'm an applications engineer here at GoEngineer, working from the Dallas office. And my background is in mechanical engineering. I did my graduate degree from North Carolina State University and focused my thesis on structural optimization for additive manufacturing. So this topic is sort of relevant, and I was glad that I could put something together to present today. Optimization of an aircraft frame. So first off, why is this important? In a typical commercial airline, there are about 60 to 100 rows in a cross-country or going above the Atlantic or something, and with considering about 4 frames per row, that's about 240 frames in each plane. Decreasing the weight of this by, let's say, 5, 10, 15% could result in fuel savings of about $100,000 over the course of when an aircraft is flown. A typical Boeing 777 weighs about 770,000 pounds, and a structural component like a frame is very representative of the entire geometry where of the plane itself, where these are weight components that need to be carried around. It's regardless of whether the flight is full or not. Also, something like space travel costs about $1,000 per pound, and hence it's very essential for anything that is aerospace related, or even other industries like medical, where weight savings is considered extremely beneficial. And that's the basis for today's webinar, where we look at topology optimization as a method for exponentially reducing the weight of our designs. So let's go ahead and get started. If you've been to a webinar before, you've probably seen the product development process, where GoEngineer offers solutions all the way from an initial conceptualization with tools like 3D scanning to design, analysis, validation, and finally manufacturing. So tools like SolidWorks, simulation, CAMWorks, flow simulation tools, of course 3D printing, which is beneficial in all of these different aspects. And today we're going to talk about solid thinking, which is conceptualization or a design that is based on analysis. And the tool that we're going to use is Inspire. So what is the thinking behind this? It is the fact that a traditional design process, which goes from concept to production, you merge the differentiation between a detailed design and validation, and you switch to a analysis based design approach. So the outline for today, we're going to look at an aircraft frame and look at an analysis based design. So this is the frame that you see on the right is one that I looked up and quickly modeled in SolidWorks. And we'll look at what changes we need to make to the model to set it up for analysis with solid thinking. And finally, we will go ahead and look at some results in solid thinking after setting up the analysis, and see what we can do to bring it back to simulation or to a CAD tool like SolidWorks. Some of the tools that we will be using today are SolidWorks for modeling. I will be doing some FEA using SolidWorks simulation, and we will also look at solid thinking for the topology optimization, which is a fancy way of saying reduction of the mass of this design itself. So to start off with, here is our original design, and I quickly set this up in SolidWorks simulation. So first off, material is going to be aluminum 6061, and quickly did an FEA, and again in this set up some remote loads, gravity, and fixed the bottom, and got some simulation results going. So if I were to switch to SolidWorks real quick, here is my initial design. Again, you can see pretty basic stuff. Not too many features in the feature tree itself. If you notice a couple of points in the coordinate systems, that's for defining the load in simulation. So switching to simulation, let's say this aircraft frame is in the middle aisle, where it's a typical aircraft with 343. Then once again, the material is defined as 6061 alloy. Since this is a part, there are no fixtures that are defined, and there are no connections that are defined. The bottom is going to be fixed. I use some split lines to define a separate face. And finally, let's look at some loading conditions. So we have gravity defined, and there's also a remote load mass option. This remote load mass is a way to apply a load at a remote location. So in this case, I have simulated the load of a person sitting, and the force is then transferred to these structural components or these faces on the top. So that's the location of two people sitting, and I took a maximum weight of about 350 pounds and found different components of it. So yeah, having said that, here are the loads, and looking at some quick results, we see that this initial configuration has a factor of safety about 1.6, which is not too high because we're still looking at only a static analysis. Keep in mind that there's a lot of vibration effects that need to be taken into account as well, and I'm not doing that in this case. So there would be additional load effects that have been ignored, and hence a higher factor of safety makes sense. So once again, this is a good initial design, and you see that there's some material that has been taken off through just intuition and previous iterations of the design. So if we were to take this one step further, how do we approach the same problem and look for a better solution in terms of reducing the weight but making sure that our design is still effective? Switching back to the presentation, we're going to make some slight changes to the model itself to create a design that I can use in SolidWorks, that I can use in SolidThinking. So once again, the original design is on the left, and you see two changes that I've made to that design. The first one is, of course, that I've filled in all the gaps. I've not made any changes. I've not attempted to reduce the weight of it. The back section is sort of cut out because that's room for the person sitting behind to keep his feet. So that's one change. And the second thing that you notice is that the part on the right is now divided into 4 different sections. You have the 2 sections in the bottom, which where our fixtures are going to be located, and then you have the region on the top that is going to be the location of the force. So this center region is what can be optimized by the SolidThinking tool. Before we switch to SolidThinking, I still want to go back to SolidWorks one more time, and let's switch to this new design. So once again, it's completely filled up, and here is a static analysis, with the same two loads. So let's go ahead and look at the loads real quick. Once again, it's the same. So I'm going to go ahead and look at some stress results. And needless to say, the stresses have gone down because now it's completely filled. So anytime you're using any numerical analysis tool, you're using a CFD tool or FEA or solid thinking for that matter, it's always recommended to have an idea, an intuition of what you expect from the results. For example, one way to kind of confirm your intuition is by looking at an animation of the deformation. So here is an animation of how your FEA analysis looks and what is expected. Needless to say, this is magnified about 92 times so that we can actually visually see it. And before we do our topology optimization, there's a couple of things that I would like to show you from a simulation standpoint that helps us gain an intuition for the results. The first one, let me hide these external loads so that it's not visually as daunting. First one is the design insight plot in SolidWorks simulation. So what this tells us is it tells us regions that are going to take up maximum load. So what we see here is the some of the regions that are going to have material for sure is going to be this top right and the bottom and the regions close to the fixtures. And another novel way, now this hasn't been done too much before, but another novel way to look at or to gain an intuition of where to place material is by looking at the principal stress plots and looking at the vector plot options for this. To define the study, once again, you can right click on results, go to define stress plot, and switch to principal stress 1, and here's your vector plot options available. And when you do this, you can look at these directions and vector plots. So a couple of things here. First off, we are looking at principal stress 1, and of course red is about 4,000 psi, and blue is minus 300. So if I look at some of the regions that are red or green, I notice that a bunch of the arrows, which are slightly bigger, are towards the bottom half of, or the bottom region of this frame. So keep that in mind. And now let's also look at stress 3. When we look at stress 3, so first off, red is a really small number, and now the green and blue is going to be slightly bigger. And we see that the concentration of arrows are on the top half, or the close to the top face, where all the arrows are kind of congregated at one place. So let's keep this in mind as we switch to the topology optimization tool. Switching back to the presentation, we're going to switch to solid thinking now and set up the same model in solid thinking and look at some results. Here is solid thinking. There's the same SolidWorks part that can be opened in solid thinking, and very similar to an FEA analysis. There are kind of 5 or 6 major things that you should do. First one is material. So we're going to go ahead and specify material as aluminum 6061. You can create custom materials as well if you wish. Next up, we need to specify what is called the design space. So you can right click on one of the parts and specify them as the design space. It turns red, and that's what tells you that that's the component that's going to be optimized by the software. There's a very intuitive user interface for applying the loads and fixtures. You're applying boundary conditions. I'm going to first start with supports in the very bottom, and then going to apply some loads. So to apply a force, I'm going to pick this face, and I'm going to change the location of the force. So we're going to move this a little bit behind, and then I'm going to randomly select regions, but this is close to what I used for the FEA analysis. And once we do that, we can specify some numbers. So once again, similar to what we did in the FEA side of things, make sure directions of the arrows are correct. And then last thing we want to do is make sure that that force is on all the faces. So the same force will now be transferred to these 4 faces. And there's a second force as well that's going to be on the same face, same set. So same thing. We're going to drag the force. This time it'll be dragged a little bit further out. So, and then pull it back a little bit more. Make sure we get the correct magnitude, and also make sure that it's acting on all 4 faces. Since the 2 forces are relatively close to each other, I want to make sure I get the numbers correct for the first one. So the first one is going to be minus 18, and the second one Alrighty, so since now that we've defined that first load, let's go to the second one and make sure we get correct dimensions for that as well. So this is further away. Alright, so that defines the 2 loading conditions. Okay, now that we've done that, we've specified the materials, we've specified the design space. Since this was actually a part, everything is going to be bonded by default. And lastly, you have meshing. One good thing about SolidThinking is you can specify manufacturing constraints using the shape control options. A single draw or a split draw or an extrusion helps you define whether it's a casting process or an extrusion based process, and that way the geometry is going to be conducive to that sort of manufacturing method. So usually a topology optimization is going to give you an organic shape, which is fine if you're going to use a method like 3D printing to manufacture it. In this case, we're not going to apply any shape controls. And finally, we get to meshing. So when you hit the little play button beside optimize, you have a bunch of different options. Once again, you have contact. This is the mesh size, which can either increase your runtimes and give you an accurate answer, or have a relatively smaller amount of runtime. And you can also include frequency constraints. Once again, if you have rotating components or you have an engine mount that you're working with, you want to make sure you avoid resonance. So that's another big one that you want to take into account. And the last thing is, by default, we're going to do a maximize stiffness. You can switch to a minimize mass and specify what's the minimum factor of safety that you want. And it's going to find a solution such that it meets that. So this study took about 15 to 20 minutes to run. So I'm going to open a study which I have already ran before. Let me go ahead and close this and open up the other study. So here's the study after it ran to completion. Once again, similar setup, and here is the optimized results. There's a slider that kind of fills or removes material based on how much fill you want. So kind of staying about 70% to the right, it still removes a lot of material. If you look at the optimized geometry, you see that it's removed materials from the insides. So at this point, typically I would use a tool called PolyNURBS. Now, what PolyNURBS is, it's a very interesting tool actually. the geometry that you get that's optimized is one that is one that is optimized from a mesh, and hence usually a lot of these topology optimization tools have a problem in working with geometry that is then workable from a CAD standpoint. So if I take this and export it as an STL, then I have a bunch of triangles which I wouldn't be able to do any other post-processing with SolidWorks or any other CAD tool. And hence, the PolyNURBS functionality is actually very useful because it lets you export geometry similar to, let's say, a parasolid model or an IGES or a step. You can even save it out the way it is and then open it back up in SolidWorks. So there's a lot of capabilities, and it also gives you a parasolid model, which is a lot easier to work with. Now, in this specific case where you have internal geometry that's hollow on the inside, but it's still occupied on the outside. So first off, here's the PolyNURBS feature where you can select a specific cross section and go through it and define geometry this way, which is pretty cool in itself and works for most features and most topology optimized geometry. But in this case, the one thing it doesn't do is it does not recognize internal holes the way I have in this model. And because of that, uh, I can still use this to define geometry on the outsides, but I wouldn't be able to take advantage of the um, internal hollow regions that are already there. So I took a slightly longer approach in this case. What I did was um, I took a snapshot of this internal geometry, and I went back to SolidWorks. And what I did was I went ahead and modeled that internal geometry. So once again, if I were to use my feature manager and show you that, here's the geometry that I designed instead of the design space. So I went ahead and used splines to go ahead and model this in, and then went ahead and mirrored it on the other side. So I still have the entire hole in the middle. And if you remember the geometry from SolidThinking, there was still regions on the inside that was completely filled. So once again, I went ahead and filled some of those regions in. So if you wanted to look at a section view of this, let's go ahead and look at that real quick. Look at the internal geometry. So once again, a very organic shape, which you'd probably only manufacture with 3D printing, but it's a shape that would result in a good 20-25% weight reduction overall. And of course, to ensure that this design still works, you would go back and do an FEA analysis with a similar setup and make sure that the stress results are not crazy high. So other than a couple of singularity regions over here, the stresses are still well within limits, and hence we know that the design is still good to go. So what are some of the changes that we saw? We saw that based on the optimized geometry, the insides were now hollow, and it's about 20% lighter than the original design. And also we validated this using finite element analysis. Once again, SolidThinking, hitting some conclusion points here. SolidThinking is a structural optimization tool which also takes manufacturing constraints into account. And that is useful because we still want to take traditional manufacturing tools into account for mass production. It has a very easy to use intuitive interface where if you've used the CAD tool before, it's going to be very easy to transition to a SolidThinking interface. And finally, it is an analysis driven design approach which is going to help with exponential weight savings. Once again, it's With years of experience, you develop an intuition on where to place material, and that is extremely important. But if you really want to push the boundaries of that, you can use that existing knowledge, but take it one step further, and use a tool like solid thinking to make sure that that you can exponentially reduce the weight. That's all I had for you today. Thank you for joining me. Once again, my name is Arvind Krishnan.